1 billion light years away, a dying star did something no telescope on Earth had ever caught in the act before. It got brighter. Then it faded. Then it got brighter again and faded again, 4 separate times, each cycle arriving a little faster than the one before it, like a heartbeat quickening in the final moments before something breaks through. Astronomers had a name ready for the general phenomenon long before they understood what was actually happening inside it. They called the pattern a chirp, borrowed from the sound of a bird call speeding up in pitch. What they did not expect was that the only way to explain that chirp would require reaching for the single most extreme equation in all of physics. Albert Einstein's general theory of relativity, invoked for the first time in the history of astronomy to describe the inner mechanics of an exploding star. To understand why this moment mattered so much, you have to go back more than 2 decades, to when astronomers first identified a strange new category of stellar explosion, one that defied the tidy rules governing ordinary supernovae. Most supernovae, spectacular as they are, follow a fairly predictable arc. A massive star's core collapses, its outer layers are blown outward in a catastrophic explosion, and the resulting fireball brightens, peaks, and then steadily fades as the debris cools and disperses. But in the early 2000s, astronomers began finding a rarer breed of exploding star, one that shone 10 times brighter, sometimes more than anything a standard core collapse could explain, and one that stayed astonishingly bright for far longer than it had any right to. Scientists began calling these superluminous supernovae, and for years, the extra energy powering them remained an open, nagging question. The explosion itself, the raw physics of a massive star's iron core collapsing under its own gravity, simply could not account for that much light, for that long, using known conventional means. In 2010, a young UC Berkeley theoretical astrophysicist named Dan Kaysen, working with colleague Lars Bildsten, proposed an answer, developed independently around the same time by another physicist, Stanford Woosley. Their idea was audacious. What if, they suggested, some of these massive stars collapsed not into an ordinary neutron star, and not quite into a black hole, but into something rarer and more violent, a magnetar. A magnetar is a neutron star of almost unimaginable extremity, typically no more than about 10 miles across, yet carrying a magnetic field hundreds to 1,000 times stronger than an already extraordinarily magnetic ordinary neutron star. And in its youth, capable of spinning more than 1,000 times every single second. According to Kaysen and Bildsten's theory, as a newly formed magnetar spins, its ferocious magnetic field could accelerate charged particles outward into the surrounding debris of the explosion, injecting a slow, steady additional stream of energy into the fireball long after the initial blast had already begun to fade, keeping the whole spectacle burning brighter and longer than physics alone would otherwise allow. It was, by any measure, an elegant idea. It solved the math. It fit the observed brightness curves reasonably well, and for 16 years it remained exactly that. An elegant idea, plausible, mathematically consistent, favored by many researchers in the field and never directly confirmed. As Dan Kaysen himself would later describe it, the magnetar hiding inside a superluminous supernova felt almost like a theorist's magic trick, a powerful engine tucked out of sight behind impenetrable layers of expanding stellar debris. Everyone suspected the engine was there. Nobody had ever actually seen it. Then, in December of 2024, a supernova appeared roughly 1 billion light years from Earth, cataloged under the unassuming designation SN 2024A5. A global network of 27 telescopes called the Las Cumbres Observatory locked onto it and began tracking its brightness night after night for more than 200 days straight. For the first 50 days or so, the supernova behaved the way theory predicted. A rapid rise to peak brightness, then the beginning of a slow, expected fade. And then it stopped fading the way it was supposed to. Instead, the brightness began to oscillate, dimming, then briefly surging back up, then dimming again in a repeating rhythm. Astronomers had glimpsed something similar before, in a handful of earlier superluminous supernovae. 1 or 2 bumps in the light, curve, typically explained away as the supernova's expanding shockwaves slamming into a nearby shell of gas, producing a brief secondary flash. But no previous event had ever shown 4 distinct bumps, and no previous event had shown a pattern where each bump arrived measurably sooner than the last, the interval between them steadily, shrinking, exactly like a sound rising in pitch. It was the chirp astronomers had been listening for, without knowing it, for 16 years. The task of explaining it fell to Joseph Farah, a graduate student working between UC Santa Barbara and the Las Cumbres Observatory, alongside astronomer Andy Howell and a small team of collaborators. Farah tried the explanations you would expect a careful scientist to try first: ordinary, Newtonian physical effects, simple geometric quirks in how the expanding debris might be interacting with itself, precession driven purely by the magnetar's own ferocious magnetic field. Each of those explanations failed to match the precise timing of the bumps. Only one model fit the data cleanly, and it required physics far stranger than anything a supernova had ever been shown to need before. Here's the picture that finally explained the chirp. When SN 2024 A5's massive progenitor star collapsed, some of the debris from the explosion did not escape outward entirely. Instead, a portion of it fell back toward the newly formed magnetar at the center, gathering into a swirling accretion disk, similar in principle to the disks of gas and dust that surround young stars or feed hungry black holes elsewhere in the universe. Because the collapsing star's material was never perfectly symmetric to begin with, this disk did not line up cleanly with the magnetar's spin axis. It sat tilted, misaligned, wobbling slightly out of true. And that misalignment is where general relativity enters the story, because Einstein's equations predict something deeply counterintuitive. About any sufficiently massive, sufficiently fast spinning object, it does not just sit inside space. It drags space itself around with it, a phenomenon physicists call frame dragging, or more formally, Lenzi-Thirring precession. A spinning magnetar, dense enough and fast enough, twists the fabric of space-time immediately around it, and that twisting motion forces a misaligned disk to wobble. As that wobbling disk swept around, it periodically passed in front of the magnetar's fierce internal engine, blocking and redirecting its light, turning the entire dying star into something like a slow cosmic lighthouse, its beams sweeping in and out of view on a fixed, repeating rhythm. And because the disk was gradually spiraling inward over time, drawing closer to the magnetar at its center, the geometry of that wobble tightened with it, and the repeating rhythm sped up, cycle after cycle, producing exactly the accelerating chirp recorded in the telescope data. Every previous theoretical model failed to reproduce that specific acceleration. Only a spinning magnetar, dragging space-time around a misaligned, inward spiraling disk, reproduced the numbers with the kind of precision that leaves little room for alternative explanation. From that single chirp, astronomers extracted numbers that sound almost fictional. The newborn neutron star at the heart of SN 2024 AFOV was spinning once every 4.2 milliseconds, more than 200 rotations every second, for an object roughly 10 miles across, meaning a point on its surface would be moving at a meaningful fraction of the speed of light. Its magnetic field measured out at roughly 300 trillion times the strength of Earth's own magnetic field, a number so far beyond ordinary human experience that comparing it to anything on Earth barely conveys the scale. It is, quite simply, one of the most extreme physical environments ever directly characterized by observational astronomy, reconstructed entirely from patient measurements of fading, flickering starlight collected from 1 billion light-years away. The significance of this discovery extends well past a single distant star, because it finally settles a genuine 16-year scientific argument. For all that time, the magnetar theory sat alongside a serious rival explanation, that superluminous supernovas might instead be powered by the explosion's shockwaves slamming into leftover material surrounding the star, briefly boosting its brightness without needing a magnetar at all. Both explanations remained mathematically viable. Both had defenders in the astrophysics community. What had never existed until this analysis was a direct, unambiguous signature that could only be produced by an actual, physically real spinning magnetar sitting at the heart of the wreckage. As one of the study's senior co-authors, UC Berkeley astronomy professor Alex Filipenko, put it plainly, what had never been demonstrated was that a magnetar had actually formed in the middle of a superluminous supernova, and that is precisely what this new analysis showed, for the first time, with data rather than inference. It is worth pausing here, because this is the part of the story that should genuinely unsettle you in the best possible way. Astronomers are not simply confirming that a rare and exotic object exists somewhere in the universe. They are confirming that Einstein's century-old description of gravity, developed to explain the orbit of Mercury and the bending of starlight around our own sun, reaches all the way out to describe the death throes of a star 1 billion light-years away, still working exactly as predicted, still bending space and dragging it into motion around an object our species did not even have direct evidence for until this discovery. Filipenko himself noted how rare and rewarding a moment like this is. Seeing a clear, unmistakable effect of general relativity is always exciting for a physicist, but seeing it for the very first time inside the wreckage of an exploding star adds a layer of significance that few discoveries in modern astrophysics can match. None of this resolves every remaining question about superluminous supernovae, and the researchers themselves have been careful to say so. Filipenko was explicit that this single, well-documented case does not mean every superluminous supernova is powered by a magnetar. Some may still be explained by the older, rival theory involving shock waves colliding with circumstellar debris. Others, according to a separate proposal from Kaysen, might instead result in a black hole rather than a magnetar, one that, if surrounded by its own misaligned accretion disk, could in principle produce a similar wobbling chirp through the same relativistic mechanism. What this discovery does confirm is that the magnetar pathway is real, that it has now been observed directly rather than merely inferred from indirect brightness curves, and that the population of superluminous supernovae, explained by circumstellar shock waves alone, is almost certainly smaller than scientists previously assumed. There's also an open question the research team could not yet answer from this single event. How common is this chirping signature actually going to turn out to be? SN 2024 AFF happened to be tracked closely enough and for long enough by enough independent telescopes that its unusual pattern could be caught, measured, and modeled with this level of precision. It is entirely possible that other superluminous supernovae have exhibited similar chirps in the past, hidden inside noisy, incomplete data that nobody had the tools or the reason to analyze this carefully. Joseph Farah, the graduate researcher who led the analysis, has already suggested that dozens more chirping supernovae may be waiting to be found once a new generation of survey telescopes comes fully online. Chief among them is the Viracy Rubin Observatory in Chile, recently completed and designed to conduct the most comprehensive, continuously repeating survey of the night sky ever attempted, an instrument expected to discover thousands of superluminous supernovae over the course of its operational lifetime, each one a fresh opportunity to listen for another chirp, another confirmation, another magnetar caught in the act of being born. To fully appreciate how strange this outcome is, it helps to understand what actually happens inside a star massive enough to produce this kind of death. A star, roughly 25 times the mass of our Sun, spends most of its life in a delicate, ongoing standoff between two opposing forces: gravity, constantly trying to crush the star inward under its own immense weight, and the outward pressure generated by nuclear fusion happening in its core. For millions of years, that balance holds as the star fuses hydrogen into helium, then helium into carbon and oxygen, and eventually, in its final stages, works its way up through progressively heavier elements, layer by layer, like an onion built from the inside out. But fusion cannot continue indefinitely. Once a massive star's core is composed primarily of iron, fusing iron no longer releases energy. It absorbs it, and in that instant, the delicate balance that held the star together for its entire life collapses, quite literally, in less than a second. The star's core implodes under its own gravity so violently that electrons and protons are forced to merge into neutrons, compressing a mass greater than our Sun's down into a sphere roughly the size of a city. Most of the time, that collapse produces an ordinary neutron star, and the star's outer layers rebound outward in the explosion. Astronomers classify as a supernova. Occasionally, if the collapsing core is massive enough, it continues collapsing past the neutron star stage entirely, forming a black hole instead. And in the rarest cases, when the original star possessed an unusually strong magnetic field to begin with, that field can become dramatically amplified during the collapse itself through processes physicists are still working to fully model, producing not an ordinary neutron star, but a magnetar, the same ultramagnetized, rapidly spinning object that Kaysen and Bildston proposed, and that Farah's analysis has now confirmed, sitting at the heart of SN 2024 AFAV. Magnetars themselves carry their own strange history within the broader story of astrophysics, and it is worth understanding why they were considered such an exotic, almost speculative, category of object for so long. The first evidence for magnetars came not from supernovae at all, but from a series of brief, intensely powerful bursts of gamma rays and X-rays detected coming from isolated neutron stars in our own galaxy, beginning in the late 1970s and continuing through the 1990s. These bursts were far too energetic to be explained by an ordinary neutron star's rotation alone, and it eventually became clear that only an almost inconceivably powerful magnetic field, orders of magnitude stronger than any other magnetic field known to exist anywhere in the universe, could account for them. It took years of careful observation and theoretical work before the astrophysics community broadly accepted magnetars as a distinct, physically real category of object, separate from ordinary pulsars, rather than some kind of unusual measurement artifact. Even after that acceptance, connecting magnetars specifically to the extraordinary brightness of superluminous supernovae remained for 16 years an unconfirmed hypothesis rather than settled fact, precisely because nobody had ever caught the moment of a magnetar's birth directly, buried as it is beneath the expanding wreckage of the star that created it. That earlier work on magnetars also connects to one of the more startling mysteries in modern radio astronomy: one that gives this discovery even more weight than it might first appear to carry. In recent years, astronomers have detected a class of extraordinarily brief superluminous supernovae, strengthens the broader case that these same objects are responsible for at least some of the fast radio bursts currently puzzling astronomers, tying together two of the strangest, most energetic phenomena in the observable universe through a single, shared type of stellar corpse. Confirmation still carries weight because general relativity makes such audacious claims about reality that each verification feels like it should not have worked, and yet somehow always does. The theory was first confirmed in 1919 when astronomers measured starlight bending around the sun during a total solar eclipse, exactly as Einstein's equations predicted, explaining subtle irregularities in Mercury's orbit that Newtonian physics could never quite account for, predicting the existence of black holes long before anyone had direct evidence they were real, and forming the theoretical backbone behind the 2015 detection of gravitational waves, ripples in space-time itself produced by colliding black holes a billion light-years away, a discovery that itself won a Nobel Prize. Frame dragging, the specific effect at the heart of this new magnetar discovery, was itself only confirmed to occur around Earth in the early 2000s, using a dedicated satellite called Gravity Probe B, which measured an almost imperceptibly tiny wobble in the orientation of onboard gyroscopes caused by our own planet's rotation dragging space-time along with it, just enough to be detectable after years of careful, painstaking measurement. That effect around Earth is almost too small to imagine. Around a magnetar spinning more than 200 times per second, packed, curve of an entire exploding star, bright enough and dramatic enough to be measured from a billion light-years away using ordinary ground-based telescopes. It is the same. The next chapter of this story is already being written, and it involves an instrument built specifically to catch far more of these fleeting, chirping supernovae before they fade from view. The Vera C. Rubin Observatory, perched high in the mountains of Chile and equipped with the largest digital camera ever constructed for astronomy, is designed to photograph the entire visible southern sky repeatedly every few nights for a full decade, cataloging changes in brightness across billions of objects with a level of consistency and coverage no previous survey has ever achieved. Superluminous supernovae are rare, but Rubin is expected to be sensitive enough and thorough enough in its repeated coverage to catch thousands of them over the course of its mission, rather than the handful that have been carefully tracked by dedicated follow-up campaigns, like the one that caught SN 2024 AFAV. Each one of those thousands represents another opportunity to listen for a chirp, another chance to determine whether this particular star's death also hid a newborn magnetar inside it, dragging space-time around itself in the dark. Farah, the researcher who first cracked this case, has already suggested that dozens of similar chirping events may be waiting inside archived data from older surveys, patterns that were recorded but never fully analyzed, because nobody yet knew what signature to search for. Rubin's contribution will not just be finding new examples going forward. It may also mean returning to the past. That fragility is, in its own way, the most humbling part of this entire story. The universe did not do anything unusual by producing a magnetar inside a dying star. Based on current theoretical models, this kind of event may be happening somewhere in the observable universe on a fairly regular basis, hidden inside the depths of massive stars scattered across countless galaxies, most of them far too distant, too faint, or too poorly timed relative to our current instruments to ever be caught in this kind of detail. What changed is not the universe. What changed is our capacity to notice this one time, with this one star, thanks to a coincidence of timing, instrumentation, and a scientist trained to recognize a signature that theory had predicted 16 years earlier, but nobody had ever actually confirmed. Joseph Farah himself put it about as well as anyone could. This is the universe telling us, loudly and directly, that we do not fully understand it yet, and daring us to keep explaining it anyway. It is worth remembering, too, just how young this entire branch of astrophysics really is. Neutron stars themselves were only confirmed to exist in 1967, when a graduate student named Jocelyn Bell Burnell noticed a strange, perfectly regular pulse of radio waves in her telescope data, a discovery initially nicknamed, half-jokingly, LGM-1 for Little Green Men, before scientists realized they had found something almost as strange as an alien signal, a dead star's collapsed core, spinning and beaming radiation like a cosmic lighthouse. Magnetars themselves were not proposed as a distinct category of neutron star until the 1990s, and were not confirmed observationally until years after that. Superluminous supernovae were not even recognized as a distinct class of another. Science, at its best, does not move in a straight line toward a fixed destination. It moves the way this story moved. 16 years of a good idea sitting untested, waiting patiently for the right star to explode at the... Consider, finally, what a moment like this actually represents about the search for understanding more broadly. Every heavy element in the universe beyond hydrogen and helium, every atom of iron in your blood, every trace of gold or platinum on Earth was forged inside the violent deaths of stars like the one that produced SN 2024 AFS, or in the catastrophic collisions of neutron stars that scientists have only recently learned to detect through gravitational waves. The same extreme physics now confirmed inside this single, distant, chirping supernova is part of the same process that built the raw material for planets, oceans, and eventually life. We are not simply observers of these events from a safe, comfortable distance. We are their downstream product, assembled from the same catastrophic stellar deaths that astronomers are only now learning to fully decode, one impossible signal at a time. There is a quieter, more personal thread running underneath all of this too, one easy to miss amid the equations and telescope data. Jocelyn Bell Burnell, the graduate student who first detected a neutron star's regular pulse back in 1967, was, for decades afterward, denied the Nobel Prize that was eventually awarded to her supervisor for the same discovery, a slight she has spoken about since with remarkable grace. Nearly 60 years later, it was another graduate student, Joseph Farah, working through mountains of brightness data collected by a network of telescopes rather than a single radio dish, who found the next piece of that same lineage of discovery. Not just a neutron star's pulse, but direct proof of the violent birth of one of its rarest, most extreme cousins. Some of the most consequential moments in the history of astrophysics have come not from senior professors leading well-funded, decades-long missions, but from graduate students willing to stare at an unusual pattern in the data a little longer than anyone else thought necessary, and ask what it might actually mean.